Hey everyone, and welcome to AI Paper Podcasts.
Glad to be here.
Today we're digging into some really interesting research, stuff that could fundamentally change how we interact with large AI models.
Absolutely. We're talking about speed.
Exactly. Ever felt like you're waiting an eternity for those giant reasoning models, those LRMs, to spit out an answer?
It's a common frustration for sure.
Well, we're tackling that head on. The paper we're dissecting, SpecReason, Fast and Accurate Inference-Time Compute via Speculative Reasoning, offers a really clever way to speed things up, dramatically even.
It's a neat idea. Think of it like having a smaller, faster assistant helping out the main model.
Right. A nimble AI helping the big guns think faster by predicting the easier steps in the reasoning process.
And the results they're reporting are pretty eye-opening.
Yeah, inference speeds can skyrocket, and get this, accuracy can actually improve.
Which is kind of counterintuitive, but we'll get into why.
Okay, so for the quick summary, the TLDR crowd listening in. Large reasoning models, LRMs, they're brilliant, but they can be slow, really slow.
Especially with complex problems requiring long chains of thought.
SpecReason tackles this using a tiny model to basically guess the in-between thinking steps.
The simpler ones, yeah.
Then a big, powerful model double-checks these guesses. Quick verification, and boom, the outcome is 1.5 to 2.5 times faster inference. Plus, potentially, a 1 to nearly 10% boost in accuracy.
That's the headline result. Pretty significant.
Okay, so that's the short version. Now let's unpack how this magic trick actually works. Why are these reasoning behemoths so darn slow in the first place?
Well, it really comes down to the way they think. You know, these long, intricate chains of thought or colors.
Right, the step-by-step reasoning.
Exactly. When an LRM tackles a complex problem, it breaks it down. It generates a sequence of smaller deductions, step by step.
Makes sense.
But the catch is, each step in that chain, each new token or piece of the puzzle it generates, depends entirely on everything that came before it.
Ah, the autoregressive nature.
Precisely. It's sequential. It can't easily jump ahead or do steps in parallel when generating that chain. And when you have these really long reasoning processes, maybe dozens or hundreds of steps, well, just adds up.
So each step has to wait for the previous one.
Yeah. And as the paper points out, for a single complex query, you could genuinely be waiting minutes, sometimes even hours in extreme cases.
Wow. Okay, that's obviously a massive roadblock for anything interactive, right? Like chatbots or real-time problem solvers.
Definitely. You just lose that responsiveness. It's not practical.
Okay, so that's the problem. Now, the brilliance of SpecReason, you said, hinges on this key observation they made, that LRM reasoning is a surprising approximation tolerance. What does that actually mean?
This is, I think, the coolest insight. The researchers found that for those intermediate thinking tokens, the ones inside the chain of thought, the exact wording isn't always critical.
Okay. Not the final answer, but the steps getting there.
Right. What really matters more is the core semantic insight, the actual logical jump being made.
Can you give an example?
Sure. Think about solving a multi-step math problem on paper. You might jot down intermediate calculations. Maybe I write 5 times 4 equals 20, and you write result is 20 from 5 by 4.
Right. Different words, same mathematical step.
Exactly. As long as those scribbles represent the same underlying operation and get the right intermediate result, you're both still progressing correctly towards the final answer.
I see.
And LRMs, it turns out, show a similar tolerance. The meaning, the logical function of that intermediate step seems to be more important than the precise sequence of words used to express it.
Okay, that makes sense. It's exploiting this inherent flexibility in the reasoning process itself.
You got it.
So how does SpecReason actually put this idea into practice? Walk us through the two-model system they propose.
So SpecReason uses this two-pronged approach. You got two main players. First, there's a lightweight, much faster speculator model.
The little helper.
The little helper, yeah. This smaller model looks at the reasoning the main model has done so far and tries to predict or speculate the entire next logical step. It makes an educated guess.
Okay, so it generates a whole chunk of text representing the next thought.
Typically, yes, a reasoning step. Then comes the second player, the powerful base model, the big LRM.
And its job is?
Its job here isn't to generate the step itself initially. Instead, it quickly assesses the utility or the quality of the step that the speculator just proposed.
Ah, so it's like a gatekeeper, a quality check.
Exactly, it's judging. Is this speculated step actually helpful? Is it moving us in the right direction towards the final answer?
And what happens then after the base model makes its judgment? Is it just like a simple thumbs up or thumbs down?
Pretty much, yeah. Based on that evaluation, the speculated step is either accepted or rejected.
Okay.
If it's accepted, if the base model thinks it's good enough, the system just adopts that step and moves forward. The small model then gets ready to speculate the next step.
Saving a lot of time, presumably.
Hopefully, yes. But if the base model decides, nope, this speculated step isn't quite right, or maybe it's just not useful enough,
Then what?
then SpecReason rejects it and falls back. It reverts to the main base model to actually generate that reasoning step properly from scratch in its usual autoregressive way.
I see. So you still maintain the accuracy and the power of the base model when needed.
That's the key. You ensure the integrity of the reasoning process.
Yeah.
The heavy-duty thinking still falls to the base model when things get tricky or the speculator messes up.
But the hope is that the smaller, faster model can handle a good chunk of the intermediate steps, maybe the more predictable ones.
Exactly. That's where the speedup comes from.
Now, the paper mentions this needs efficient verification. That assessment by the base model has to be fast. Otherwise, you've just created a new bottleneck, right?
Absolutely crucial. If the check takes as long as generating the step, you gain nothing.
So how do they make it fast?
Well, instead of having the base model fully regenerate the step to compare, or, doing complex analysis, they use a single, efficient pre-fill pass.
Pre-fill pass.
Yeah. Think of it like the base model quickly glancing ahead based on the speculator's suggestion and saying, yep, that seems plausible, or, maybe not. Computationally, it's much cheaper than full generation.
How cheap are we talking?
They have a neat implementation where they prompt the base model using the existing reasoning history plus the speculated step to generate just a single token representing a score.
A score, like 0 to 9 or something.
Exactly like that. They use 0 to 9 in the paper. A single token output that quantifies the utility of the speculated step.
And because it's reusing the previous context and only generating one score token?
It's very fast. The computational cost is similar to the base model, just generating 1 or 2 tokens itself. Much, much faster than generating the whole reasoning step.
Gotcha. And this score then gets compared to some kind of threshold.
Yep. They use a static acceptance threshold in the paper. Let's say the threshold is 5. If the base model outputs a score of 5 or higher for the speculated step, it gets accepted.
And it's 4 or lower.
Rejected. And the base model takes over for that step.
And you can adjust this threshold, presumably.
Absolutely. That's the tuning knob. You can adjust it to control how aggressive the speculation is. A lower threshold means accepting more speculated steps, potentially faster, but maybe slightly riskier in terms of step quality.
While a higher threshold means being more cautious.
Right. More cautious, maybe higher quality steps get through, but potentially less speed up because the base model does more work. The authors also mentioned you could use more sophisticated methods too, like looking at token probabilities or even dynamic thresholds. But this simple scoring worked well.
Okay, this whole idea, it sounds a little bit like speculative decoding, which people might have heard of for speeding up standard text generation. How is SpecReason different?
That's a really good question, and it highlights a key difference. Traditional speculative decoding, the kind used for, say, faster chatbot responses.
Yeah.
That usually focuses on predicting the final output tokens. A small draft model generates tokens, and the base model verifies them, usually requiring an exact match at the token level.
Okay, so it's about getting the final words right faster.
Exactly. SpecReason, on the other hand, is targeting those internal thinking tokens, the chain of thought itself. And crucially, it's looking for semantic alignment or utility, not necessarily a perfect word-for-word match.
Ah, back to that approximation tolerance idea.
Precisely. Because the reasoning process can tolerate some variation in phrasing, SpecReason doesn't need that strict token-level match. It's checking if the meaning or the logic of the speculated step is sound and useful.
So speculative decoding is token-level, final output focused. SpecReason is semantic-level, intermediate reasoning focused.
You've got it. That difference in focus is what lets SpecReason exploit the nature of reasoning tasks specifically.
That makes perfect sense. And the paper also mentioned these two techniques aren't mutually exclusive. They can actually work together.
Yes, they're quite complementary because they operate at different levels.
How would that work in practice? Like a hierarchy?
Exactly like a hierarchy. You could have SpecReason working at the higher level, speculating entire reasoning steps.
Okay.
Then, if SpecReason rejects a step and the base model needs to regenerate it, well, during that regeneration process by the base model, you could then apply standard speculative decoding to speed up the generation of the individual tokens within that step.
Whoa, okay, so it's like acceleration layered on top of acceleration.
Potentially, yes. You get speed boosts at the step level from SpecReason, and then potentially more speed boosts at the token level from speculative decoding when the base model is doing its work.
That sounds like a really powerful combination. Okay, let's shift gears to the proof, the evidence. What kind of models and benchmarks did they use to put SpecReason through its paces?
Right, the experiments. For their main results, they used a QWQ32B model as the base model. That's a pretty strong reasoning model.
Okay, 32 billion parameters.
And for the lightweight speculator, they used a distilled version of DeepSeek R1, a 1.5 billion parameter model, so significantly smaller.
Distilled meaning trained to mimic the larger one, sort of.
Yeah, trained on outputs from a larger model to be smaller but still capable, especially on specific tasks like reasoning steps here. They also did some tests with a much bigger base model, an R170B, to see how it scaled.
And the tests themselves, what kind of problems?
They used a pretty challenging and diverse set of reasoning benchmarks. There was AIM, which is Advanced High School Math Competition Problem.
Good stuff, definitely.
Then Math 500, another complex math data set, and also GPQA Diamond. This one has graduate level questions across physics, chemistry, biology, really pushing the reasoning limit.
And how did they measure success? Just speed?
Speed was key, obviously, measured as latency reduction. But they also tracked accuracy carefully, using pass at 1. That means they generate multiple potential solutions or reasoning paths and check if at least one of them gets the correct final answer.
Okay, makes sense. So what were the big results? Did it work?
It did, yeah. The results were quite compelling, actually. Across those benchmarks, SpecReason consistently gave significant speedups. They reported between 1.5x and 2.5x reduction in inference latency compared to just running the base QWQ32B model normally.
1.5 to 2.5 times faster. That's substantial.
It really is. And maybe even more surprisingly, they saw accuracy improvements.
Right. You mentioned that earlier. How much?
Ranging from 1.0% up to 9.9% improvement in pass at 1 accuracy.
Wow. Why would it get more accurate?
The researchers suggest it's because of that explicit judgment step. The base model, acting as a gatekeeper, might actually help filter out potentially flawed or less productive reasoning paths that the base model might have otherwise explored on its own. It adds a layer of scrutiny.
Huh. An unexpected bonus.
Kind of, yeah. And when they combined SpecReason with speculative decoding,
A hierarchical approach.
right, they saw even bigger latency reductions on top of what speculative decoding alone provided, ranging from an additional 19.4% to 44.2% faster.
So the two methods really do complement each other well.
Seems so. Interestingly, the biggest speedups, the 2.5x factor, were seen on the math dataset.
Any idea why?
Their hypothesis is that the performance gap between the small 1.5B speculator and the 32B base model was maybe smaller on math problems compared to, say, the GPQA questions.
Meaning the speculators' guesses were good more often.
Exactly, leading to a higher acceptance rate for the speculated steps and therefore more speedup. They also noted the actual percentage of steps handled by the small model varied quite a bit depending on the data set and the difficulty.
Okay, so it sounds like there's this balance, this trade-off between speed and accuracy, and SpecReason gives you that tuning knob, the acceptance threshold.
Precisely. By tweaking that threshold for the base model's utility score, you can directly control that trade-off.
So lower threshold.
Lower threshold, the system is more aggressive. It accepts more suggestions from the speculator, likely faster inference.
Yep.
But maybe you risk accepting a few less than perfect steps, which could slightly hurt accuracy in some cases, though they saw improvements overall.
And higher threshold.
Higher threshold, this system is more conservative. It only accepts the steps the base model rates very highly. This likely slows things down a bit, as the base model has to step in more often.
But it could potentially boost accuracy even further.
It could, yeah, by ensuring only really high-quality intermediate steps get used. The paper actually shows graphs for subsets of math and AIM, demonstrating exactly how changing the threshold, say from 3 to 5 to 7, impacts both latency and the final accuracy. It lets you pick your operating point.
That's useful. Now, you mentioned they also tested this with a much bigger model, the R170B. How did SpecReason perform at that scale? Were the speedups still significant?
Yes, they were still significant, which is important. They reported a 1.5x speedup on the AIM benchmark using the 70 billion parameter base model.
Okay, 1.5x is still good, but it's less than the up to 2.5x they saw with the 32B model.
Right, somewhat smaller gains. The authors offered a couple of potential reasons for that.
What were they?
First, these really large models, like a 70B parameter 1, often run on more powerful hardware setups with more parallelism. This means their inherent time per token, just how long it takes them to generate stuff normally, is already lower.
Ah, so there's less room for relative improvement by offloading.
Kind of, yeah. The baseline is faster, so the relative speedup might look smaller. Second, because the R17B is just a much stronger model than the 1.5B speculator.
The quality gap is bigger.
Exactly. So to maintain high accuracy, they likely needed to use a stricter acceptance threshold, a higher bar for the speculator's suggestions.
Which means fewer speculated steps get accepted overall.
Fewer accepted steps means less offloading, and thus a somewhat smaller overall speedup compared to the scenario with the 32B base model where the gap was smaller.
That makes a lot of sense. The better the base model, the harder it is for a small model to contribute useful steps that meet the quality bar.
Precisely.
Okay, but a critical piece here is trusting that base model's judgment, right? That 0 to 9 score. How did they actually check if the base model is a reliable judge of reasoning quality?
That's a great point, and they get a clever experiment to validate this. They basically compared the utility scores generated by their QWQ32B base model with scores generated by a completely separate model called MathShepherd. Now, MathShepherd is a process reward model, or PRM.
A PRM, what's that?
It's a model specifically trained to evaluate the quality of individual steps in a reasoning process, in this case, for math problems. It's like an expert judge for mathematical reasoning steps.
Okay, so they compared the base model's quick score with this specialized judge's score for the same reasoning steps.
Exactly. And what they found was a strong correlation between the two sets of scores. Especially for steps that the PRM identified as being low quality, the base model also tended to give low utility scores.
Ah, so the base model, even just generating that single score token, was pretty good at spotting the bad steps.
It seems so. It suggests the base model itself, without needing explicit reward model training for this task, can effectively approximate the judgment of a specialized PRM. It can reliably assess the usefulness of those speculated steps.
That's really solid validation for their core mechanism. Impressive.
Yeah, it gives confidence that the verification step is actually meaningful.
Now, the paper also briefly mentioned other ways people are trying to speed up LRM inference. What are some of those other approaches, and how does SpecReason fit in?
Right, they touched on related work. There are a few different angles people are exploring. One approach they mentioned from the SkyT1 Flash team involves fine-tuning models to be more concise in their reasoning, basically teaching them to cut out unnecessary steps.
Trying to shorten the chain of thought itself.
Exactly. Another approach, called dinosaur code, tries to get the model to recognize when it's confident enough about the final answer and just stop reasoning early. An early exit strategy.
Okay, different strategies.
Yeah, and the authors position SpecReason as distinct from these. It's not about shortening the reasoning or stopping early. It's about accelerating the generation of the intermediate steps by approximating the easier ones.
And potentially complementary, right? You could imagine combining these.
Absolutely. They suggest SpecReason's approach is complementary and could potentially be used alongside techniques like early exiting or chain of thought pruning for even greater efficiency gains down the line.
Okay, cool. So let's try and bring this all together then. For our audience, the technical folks listening in, what are the main takeaways from this deep dive into SpecReason?
I think the core takeaway is that SpecReason offers a really promising and actually quite novel way to significantly speed up inference for these powerful large reasoning models.
By cleverly using that small model, big model guru.
Right. Using the small speculator for the potential easy wins, the intermediate steps, and then relying on the big base model for that efficient, fast verification. It's a smart division of labor.
And the results speak for themselves, substantial speedups. 1.5x to 2.5x.
And sometimes even those surprising accuracy improvements, which, has really significant implications for making these complex AI models more practical, more responsive for actual applications people want to build.
Yeah, getting answers in seconds instead of minutes makes a world of difference for user experience.
Yeah, totally.
And the fact that it seems to work alongside other techniques like speculative decoding is also huge. It suggests we could see combined strategies pushing efficiency even further.
Absolutely. It really points towards a future where, hopefully, the amazing reasoning power of these huge models becomes much more accessible, much less computationally bottlenecked.
So for those of you listening who are really deep in this space, maybe working on model optimization or deployment, a key question this paper raises is how you might optimize this further.
Right. Like, how does the specific choice of that small speculator model impact performance? does it need to be trained in a special way?
Or how could that base model verification step be made even smarter? Maybe different scoring mechanisms for different types of reasoning.
Exactly. And what are the practical challenges in deploying a system like this in a real-world, maybe high-throughput setting? Managing two models, the thresholds.
Lots to think about. And the researchers have actually open sourced SpecReason on GitHub, which is great.
Yeah, that's fantastic. It lets people really dig in, try it out, maybe build on it. Exploring the code is probably the best way to get an even deeper understanding.
Definitely. We'll make sure to put a link to that in the description for anyone who wants to check it out.
Great.
It's really clear that making these incredibly powerful AI models faster and more efficient is a massive focus in the field right now. And SpecReason definitely looks like a significant and pretty clever step in that direction. Thanks so much for breaking it down with me.
My pleasure. It was fun to discuss.